Mrs. Stites, and I am going to be your pre-calc teacher for this year. Go ahead and grab your beautiful blue semester 1 packet. Just hit my microphone. Oh well. That I spent many hours copying for you. These note sheets will probably be modified as we go along. Given the time constraints of getting all these materials ready for you, I just copied what I had and we'll make modifications with them as we go. All right, so let's go ahead, open up your packet to the first lesson, 2.1 functions. Get excited. So here's our first new lesson, functions section 2.1, and we will be spending 2 separate lessons on 2.1. And today we're mostly going to be reviewing domain and range. You learned how to do set notation last year, but I'm going to introduce you to something called interval notation, which is used a ton in pre-calc and a lot in calculus. So while set notation is still fine, I want you to start getting used to this new way of writing domain as well. Okay. So we know that a function is a relation in which each input has exactly one output, and you have your definition for domain and range here, which should look familiar. Something else that should be familiar is what is called the vertical line test. And the vertical line test is going to be used to determine if a graph represents a function or not. So for example, basically you have this parabola here. You're going to draw a vertical line through different parts of the graph. And because we are only hitting one location on the parabola at a time, we would say, yes, this is a function. Okay, so as opposed to this graph right here, when we draw our vertical line, you can see we have hit 2 locations. That means that for this one input value, this one x value, there are 2 different outputs, 2 y's. So this is not a function. And then if you look at your piecewise function for this last one, for these guys, you want to look at the places where the branches separate, they're like boundary lines. So for example, here you have a dotted an open and a closed dot. So that's okay. That part is fine. But over here, when we draw a vertical line, you do have 2 closed dots. So that means that this whole thing is not a function. All right. So now, if we go down and we look at these equations, you should be able to determine if it's a function even if you do not have a graph. One way to do that is to solve for y. So in number 1, if I wanted to solve for y, I would just go ahead and subtract my 2x squared over, and then I'm going to square root both sides. Do not forget your plus or minus. Okay, a lot of people forget that. And the reason that plus or minus is so important, especially in this case, is this is saying that we have 2 different outputs. Okay, so for one x value, you have 2 different outputs, which means that this is not a function. And this would actually be the graph of an ellipse, something like that, which we will discuss more when we get to conics, which is second semester. Okay. Whereas number 2, this should be an equation that you already recognize, just based on the fact that it's a y equals x squared. So you could just say, oh, well, this is a parabola, right? And I mean, that's not the exact parabola, but that's what a parabola looks like. So just like this graph up here, and since they are the same, this would be a function. And you can say, because the graph passes the vertical line test. Okay, so you just want to make sure, if you look at my directions here, that you justify your answer algebraically and in words. So graphically, we can, for this situation, that counts as your algebraically. And then just in words, you're saying, hey, it does pass the vertical line test. Whereas for number 1, your algebraically is actually showing this math. But then in words, you're telling me that that plus or minus means you have 2 different outputs. So again, one of the big things with this class is some people make the mistake of, oh, well, you know what I mean. Well, no, my job is to make sure that you know what you mean. So you do have to explain your answer to me in words to show that I know that you know what you're talking about. All right, and usually the directions will state that for you. All right, next, evaluate the following given this function. So notation is something really important in pre-calc. You want to make sure that you use correct notation now, and that way your life is going to be a lot easier when you get to calculus next year. So f of 0, that's simply saying we're plugging a 0 in place of all of our x's. You do want to make sure that you label this as f of 0, not f of x. Okay, and we're just going to show the work. All right, and of course we're going to have some cancellation occur, and you'll just get f of 0 equals -4. Okay, and it is nice to have that f of 0 equals, not just equals -4, to actually have that whole label. Now, for f of -x, this is a little different. You might not have done one like this last year, but it's essentially the same idea. Instead of plugging in a 0 for x, you're plugging in a -x in place of x. Okay, so let's go ahead and see what that looks like. Okay, so I'm just going to plug it in. And we do want to simplify this. And when we square -x, we will get a positive x squared, and then a -2x, and then a -4. Okay, and this is fine. You're not always just going to get a number or a numerical value. Okay. Now, this next one, they look similar, but they're actually quite different. When we get to 2.6, we'll talk about transformations, and we'll discuss the difference between f of -x and negative f of x. But for simply right now, in terms of finding the function, this really means we're just doing -1 times f of x. So you are just going to distribute a -1 to the whole function. Be careful. This is where people start to make errors with their distributing. A lot of algebra errors happen in pre-calc. All right, so let's see. You should have a +4 there. Okay. All right, and the last one of these, f of x plus h. Same idea as a and b. Instead of plugging in an x, or excuse me, at least in b a -x, we are now plugging x plus h in place of x. All right, so this is going to look a little weird. It's going to look like this. 3 quantity of x plus h squared, right? Because it's 3x squared. So it's becoming 3x plus h squared plus 2 x plus h. All right, every x is being replaced, -4. All right, and now we will go ahead and we get to FOIL, which I know you have been waiting all summer to do, is to FOIL. All right, so here we go. We're gonna FOIL first. So x squared plus 2xh plus h squared. And then we're gonna do some distributing. Oops, that's supposed to be a 2. And then we'll distribute our 3. So 3x squared plus 6xh plus 3h squared plus 2x plus 2h minus 4. And in a perfect world, there would be like terms, but I don't think there are any. So you're just going to leave it like this. Okay, and there you go. That is your answer. All right, last thing we're going to talk about today is domain. And we are going to discuss specifically set versus interval notation. Now, before we talk about the difference between set and interval notation, we need to talk about the two big things that cause domain restrictions. Okay, so number one, we know we can't have a 0 in the denominator of, any equation, right? So number one, no 0 in the denominator. All right, the other big one is that we can't have a negative underneath an even root. Usually we're dealing with square roots, but you can have other even roots as well. Okay, so that's the other, no negative under an even root. Periodically, these two things combine. You have both of these situations occurring, so we're going to have to be careful about that. Basically, in general, if neither of these things are happening, then our domain is all real numbers. Okay, so number 4, for example, this is a parabola. All right, and if you think of parabola, it's a smooth curve. There really isn't anything x can't be. There's no denominator, so we can't have a 0 in the denominator, and there are no even roots. So this, what you would have written in the past for the domain, and I like to put a D first for domain, is x such that x is an element of all real numbers. And some of your teachers might have used a line here instead of the colon. However your teacher did it is fine. This is set notation. So interval notation looks like this. To show all real numbers, we would say negative infinity to infinity. So what this is basically saying is x can be anything between negative infinity and positive infinity, and we're using parentheses to show that we're not including those values because infinity and negative infinity, like, they're not technically values. Okay, so either of those notations are completely fine to say all real numbers. People always say, well, do I have to pick one? No, you don't. Personally, I tend to use interval notation unless for that specific problem it's easier to use set notation. So you'll see an example of that in a few minutes. All right, next. Number 5, when you look at this, you should notice you can factor the denominator, and that is a useful thing to do to help determine your domain. All right, so once you do that, you can say, oh, well, if x is 2 or negative 2, we're going to have a 0 in the denominator, right? So that would be an issue. So the domain that you would be used to writing would be like this, x such that, and again, you can write like that, x is not equal to plus or minus 2. Okay, again, this would be set. And for this type of problem, I do prefer set notation because here's how you would do interval notation. What you're going to do is you are going to list all of the values that x can be. So here's how you would do that. You would say x can be anything from negative infinity all the way to negative 2. But it can't be negative 2, so I'm putting in parentheses. But it can be anything between negative 2 and positive 2. But it can't be either of them, so that's why I'm using parentheses. But wait, there's more. X can also be anything between 2 and infinity, but it can't actually be either of those specific values, so we're using parentheses. So what's nice about set notation is you can specifically say, like, hey, it's everything except this. Whereas with interval notation, you're showing all of the values that it can be. So when you do have just these like 1 or 2 restrictions, it becomes a lot more obnoxious to write it in interval notation. Okay, all right, so there's that one. Next, we have a square root in the denominator. So for this one, you should know that 5x minus 4 has to be a positive, right? It also has to be greater than a 0. It has to be greater than 0 because we're in the denominator. So we'll just go ahead and solve this. And we get x is greater than 4/5. So your old set notation, you would just say x such that x is greater than 4/5. Cool. And for interval notation, you would say x has to be greater than 4/5. So we would say x can be anything from 4/5 to infinity. Okay? Now, I want to modify this problem slightly. New problem. Let's say you just had this. All right, now x can, or 5x minus 4, it can be 0, right? Because this is no longer in the denominator. g of x could just be 0. So we would have 5x minus 4 is greater than or equal to 0. And when you solve it, you would get a greater than or equal to 4/5. The way this would change your interval notation would now be a bracket 4/5 to infinity, because it can be 4/5. Infinity and negative infinity will always have parentheses around them though. Okay. All right. Last one. You are going to get to factor some more. Oops, turn off that video. And let's see here. Multiplies to 2x squared. That's going to be a 2x and an x. Multiplies to 3. Well, those only options are 3 and 1. I'm going to try that, and I want it to be a 5x. So let's see, this would be a 6x and a 1x. So I want the 6 to be a positive. Positive 6x minus 1x is 5. So all right, there you go. I have factored it. And if you would like, you may notice that those 2x minus 1s are going to cancel. All right. However, and this is important, those 2x minus 1s are still going to be important for our domain. All right. X can still not be 1/2. And then over here, x cannot be negative 3. Because again, when you have those values of x, you would get a 0 in the denominator. If you remember from last year, those 2x minus 1s, they would represent what's called a hole. We'll talk about those more in our next chapter. You'd have a hole at x equals 1/2, and then to find the y coordinate, you would plug the 1/2 back in to the simplified function. Okay, but again, we'll get into that in a few weeks. So let's go ahead and let's write our domain for both interval and set notation. So set, which is probably what I would use for this, I would say x such that x is not equal to 1/2 negative 3. And I don't care what order you put those in, it doesn't matter to me. If you were doing interval notation, we would say, all right, well, x can be anything from negative infinity to negative 3, right? But it can also be everything, so that's my union, between negative 3 and 1/2. But it can't be either of those. And then also anything between 1/2 and infinity. Okay? So, all right, there you go. That is your first lesson. You have survived. And stay tuned for our next lesson, which is continuation of functions, and you're definitely going to want your calculator for it. All right, let me know if you need anything. Have a great day.